Okay, so now we just learned about Frobenius' theorem, which allows us to find a power series solution of a differential equation about a regular singular point. And by the way, the differential equation is a second order linear differential equation. Okay, and I should mention too, you know, in this format, the second order differential equation here, okay, that is, let me find it here. It's, sorry, hold on. Let me go up here. Right. So, hold on, let me take off, let me cancel this. Sorry, class, let me remove the highlight here. Okay, so, yeah, this here is the second order differential equation. No, sorry, let me bring this up. Yeah, this here is the second order differential equation, second order linear differential equation that you're finding a power series solution for. And remember again that the coefficients of y double prime and y prime and y can be functions of, they're functions of x, but they're not, they don't have to be constants. Okay, you don't have constant coefficients. You don't have that. What I'm trying to say is this is a very general approach because it allows the functions in front of the coefficient functions in front of the second derivative, first derivative, and y to be varying functions of x. Okay, all right, varying functions of x. So, okay, let me bring up the example here. Okay, so let me give you a moment to copy this example down, okay? All right. Okay, there's a chat here. Okay, good. All right, I'll give you another minute here. Very good, Christopher. Okay, so what we want to do here is we want to use the method of Frobenius to find two linearly independent solutions to this second order differential equation about the regular singular point x equals 0. So you could prove that x equals 0 is a regular singular point. You can prove that. But they're just telling you that it is a regular singular point. You'll have some problems in your homework where you'll be given differential equations and you have to classify, singular points as being regular or irregular. And you would just go through the process that we outlined in example 1 from the textbook. This problem, though, we're being told we have a regular singular point, and we need that in order to use the method of Frobenius. All right, so now, are there any questions before we move forward with the solution? Okay, very good. So, okay, what's the power series solution look like? What's the power series solution look like? Okay, so now hold on, class, one moment. All right, so this x to the nth power times x to the half power here, don't worry about that right now, okay? Don't worry about this right now. Focus on this here. So Frobenius' theorem says that the power series solution, okay, the power series solution y would be the power series n equals 0 to infinity with terms where you have c sub n times x minus x sub 0 raised to the n plus r power. Now the r power, we're going to find that later. Okay, but this is the Frobenius' theorem. Okay, which is theorem 6.3.1, right? And in Frobenius' theorem, okay, so in this case, what's x sub 0? Well, x sub 0 in this case is going to be 0. Because 0 is the regular singular point. That's your x sub 0. Hence, this is how then we get this power series. Because if x sub 0 is 0, then you're just going to have x minus 0 to the n plus r power. And then that's just x to the n plus r power. Okay, Matthew's comfortable with that. Excellent. And that's, that's how I get this here. All right, well, all right. So our power series solution takes this form. And naturally, just like you learned in section 6.2, you have to take a first derivative of the power series and a second derivative of the power series. Okay, and if you do that, then these are going to be your expressions for the first and second derivative. Are there any questions on those two? Y prime and Y double prime. Okay, very good. Well, now what we have to do, we do the same thing we did, same procedure as you did in section 6.2. We're going to substitute in the power series into the differential equation. Okay, we're going to substitute into the differential equation. And we know on the right-hand side here, there is an equals 0. We know that for the differential equation, and we'll get to that later. But let's just focus on the left-hand side of the differential equation. Left-hand side of the differential equation, I substitute in the power series for y double prime, y prime, and y. This is my result. And then, of course, what I want to do here is the next order of business is to take 2x squared. That's not dependent on n, so you can bring it inside the power series. And similarly here, the x, I can bring that inside the power series, and I would multiply that by x to the n plus r minus 1, right? And the same thing with x squared plus 1. We'll distribute that in the power series. And when we do that, we're going to get then 4 power series. The x squared plus 1 is going to give us 2 power series when we distribute it in the power series. Okay, so let me just let you copy this. All right, and let me know if you have any questions. Okay, very good, excellent, Matthew. And let's see, we'll give folks a moment to just, look at this result here. Okay, are there any questions before I go to the next page? Let me ask you, what do we have to do next? Now that we're here, what's going to come next? Good, Hugh Young. We have to have x to the kth power for all my exponents. Okay, and so here we would let k equals n, right, for all the power series that have x to the n plus r power. But for this power series here, where we have x to the n plus r, hold on here, one moment, class. One moment. Got to be a little bit careful here. One moment. You're right. Good catch, Zachary. I meant y equals k equals n plus r. Absolutely right. And then so if k were equal to n plus r, then this power series here, notice that n equals 0, right? They all start with the same index, n equals 0, but we want to get the powers to be the same. So we're going to let k equals n plus r for all of them, but that means here, this third power series is going to be x to the sub k plus 2. No, we don't want to do that, Zachary. Good question. We don't want to do that because they all have the same starting index at n equals 0. So we're only gonna let k equals n plus r, period. We're just gonna let k equals n plus r. But if we do that, then this power series here is hold on here now. One moment here. I'm hold on. I'm having a one moment. I don't like what I said here. I don't like what I said. No, scratch that class. That's wrong. That's wrong what I said. That's wrong. I'm sorry. Let's start fresh. So everything's good up to here. But you'll notice that x to the n plus r can be written as x to the n times x to the r, right? X to the n plus r power can be written as x to the n times x to the r. Now, as x to the r, and you'll notice that like for here, I want to show this before we go to the next page. I want to show this before we, come on, give me some blue here. Give me some blue. I don't know why it's acting up here. Hold on. Okay. Here you have then x to the n plus 2 times x to the rth power. Okay, so for each one of these power series, we can write the power term as I'm showing you here. Each power series term has in it an x to the rth power, right? That's in common between all the power series terms, x to the rth power. When we see something in common, what do we want to do with that? What do you think we can do with x to the rth power, since it's in common between all the power series? What can we do with that term? Factor it out. That's exactly right. That's exactly right. And that's what we're going to do. We're going to factor that x to the rth power out from all the power series. And we can do it because we can bring it out in front of the power series. X to the rth power can be brought out in front of every power series because x to the rth power is not dependent on n. So this means then that we can write our power series as you see here. As you see here. I factored out the x to the rth power from all 4 power series, and so I have x to the 4th power times this sum of 4 power series. And now at this point, that's when I'm going to start changing my index. I'm going to change my index appropriately so that all indexes have an x to the kth power in them. Okay, so hopefully now then you're okay getting down to this step here. So this is like, you know, same kind of thing you did in section 6.2. You're adjusting the power series. So of course, if like in the first power series, if k equals n, then n plus r becomes k plus r, right? And n plus r minus 1 becomes k plus r minus 1. All right. In the third power series, if k equals n plus 2, then that means that n, just in the third power series, n equals k minus 2. And that's how you get k minus 2 here. Are there any questions here to that step? All right. Well, now in this step, you have 4 power series. Which power series rules? Which is the power series? We want to combine the power series. We got to pick a starting index. The power series with k equals 2, since that's the highest index value, that's what we have to use to combine the power series. So that means the first power series that starts at k equals 0, I have to write out the first 2 terms for k equals 0 and k equals 1. Okay, and that's going to be this term and this term. Okay, and let me just see here. Yeah. Right, and then you got the rest of the power series. So you have to do this for the first power series, the second power series, and the fourth power series. You have to write out the first 2 terms of each of those power series, and then the rest of the power series. Okay. All right. So long as we're kind of organized, if we're organized, we're going to be okay. We're going to be all right. Now, what we want to do is we have in here, okay, in our differential equation with the power series in it, we have a lot of terms that can be combined. I mean, of course, we want to simplify what's in these parentheses here, and we want to combine the power series too. Power series now all start. What I'm trying to say is we have 4 power series that start at k equals 2. So we want to combine those power series and simplify the rest of it. Okay. And by the rest of it, I mean, of course, this here, and this here. So may I go to the next page to do that? Are we okay? All right. Okay, well, then let's go to the next page. Okay, so now here is my differential equation where I'm combining the 4 power series starting at k equals 2. And then I just show a little bit of algebra here to help you then see how we get to the next stage, how we get to this. Absolutely fascinating.
In that second step, there should be a wait. Oh, I see how you did it. Never mind. Sorry.
Okay. Okay. So now we're here. We're here, and this is just algebra. This is just algebra. So I'm going to combine then. I'm going to combine the 2c sub 0 r squared minus 3 sub 0 r plus c sub 0 and the 2 c1r squared plus c1r. Okay, and remember there is an x here. There is an x there. And I factor out a c sub 0 over here. And that gets me down to here. And now remember, the differential equation is being set equal to 0. Okay, now let me just see here. I think there's, let me see, one moment here. I do need, class in the notes, there should be a closing parentheses here. There should be a closing parentheses. Let me just double check this. Yeah, there should be a closing parentheses here. So please put that in your notes, class, these closing parentheses, okay? And then there's a closing parentheses here as well. Okay, so let me make sure they're in my notes too. And what I'm going to do is I'm going to simplify this this expression here, the coefficient of x to the kth power. I want to simplify that. And so what I do is I note that, let's see here, one moment.
But in this step, all these simplifications, they should all still be multiplied by x to the k, correct?
That's correct. That is correct. All I'm doing is, in the simplification, it's just like just this part. Right, right. And let me just peek at it here real quick. Yeah, so you see here how I have a c to the k there, and a c to k there, and a c to the k there, with a 1 in front of it, right? So that's how I get then this expression here that has the ck on it. And then what I do is I factor out a k plus rth power. The reason I'm doing this, class, I'm sorry, I factor out, yeah, a k plus r factor there, and that goes here. And then I can simplify all this in here to get, let me see here. Am I missing? I think I'm missing a parentheses here. Hold on, everybody. Yeah, there should be a parentheses right here as well. Right there. One moment, class. Let me put it in. Let me put it in my thing here. Hold on. Now, hold on. No, wait.
No, there
Uh,
shouldn't be a
no,
parenthesis there where you.
you're right. I had it right originally. Thank you. Now, should the two distribute? Zachary's asking, should the two distribute? Which two, Zachary? Oh, the two here. The two here. Okay, right here. I don't know why this. Yeah. This two, I don't know why this. Okay, I don't know why this. Yeah, this two here, I put it here. Okay, you're good. All right. So now what happens is I have, I mean, this, remember, this differential equation on the, hold on here, parenthesis here, right? This whole left side is equal to 0. So that means that this has to equal 0. Check. This coefficient, well, this coefficient of x has to equal 0 because there's no x term on the right-hand side here. And of course, the coefficients in the power series, coefficients of x to the kth power, they also have to equal 0 for k equals 2, 3, 4, and so forth. Okay, so let's make sure we're good. And may I move to the next page? Okay, all right, Andrea. Now I might, I try very hard, I know our class ends at 6:15 and we ought to be able to finish this by then, but if I run over a few minutes, I appreciate that many of you, most all of you really, have been staying an extra couple minutes, and I appreciate that. Sometimes of course I welcome questions, but then it delays things a little bit, but that's okay. Questions help the lecture, helps everybody. So I appreciate your flexibility. Okay. All right. All right. So Andrea's making sure she's comfortable here. And let me know when I can go to the next page. Now I want to mention something here. Okay. So we have to now solve for R. In order to get a specific power series solution, we have to solve for R. Okay, excellent. And what we're going to do is we're going to focus on this first equation here. Now, to solve for R, we're going to say we're not going to let C sub 0 equal 0. Because if we do, then we can't solve for R. okay, we're instead we're going to say C sub 0 is not equal to 0. Let's assume that C sub 0 is not equal to 0. Okay, we could, for instance, say that I want to say this the right way. We could let's say, okay, well, later on we'll let C sub 0 equal 1. Okay, but we just don't want C sub 0 to equal 0, because that means then that this equation, 2r squared minus 3r plus 1, would have to equal 0. By this first equation, if C sub 0 is not equal to 0, then 2r squared minus 3r plus 1 would equal 0. And that's how we're going to solve for r. Okay? And this is what's called our indicial equation. So indicial equations come about from the power series. So when we put in the power series and we collect the terms, it naturally comes about. There's another way also to get an indicial equation. Indicial equation is the equation that allows us to solve for r. Just before example 3, in section 6.3, there's formula 14 that also gives you what's called an indicial equation. And you'll have a problem like that in WebAssign, and there'll be a help like a watch it video to help you with that. But right now, let's just focus on this. So now I'm going to solve this for r. I can factor this so that I get r equals 1/2 and r equals 1. So we got two values for r. Oh, that's good, because I want to have two power series solutions, right? Now, the roots do not differ by an integer. They differ, r equals 1 and r equals 1/2 differ by a fraction. So that means that two power series solutions may be found based on the theory. If the difference between the two roots were equal to a positive integer, then in that case, they talk about this just before example 5. In that case, we may or may not be able to find two solutions. But for our cases here, and for like in the homework, I think most of the homework, you'll have two series solutions. So, all right. Now the roots r equals 1/2, r equals 1. We're going to let C sub 1 equal 0. Okay, so obviously, since C sub 0, we didn't let that equal 0. We're going to let C sub 0 equals 1 later, but then C sub 1 we'll let equal a 0. So this is like what you did in section 6.2 for those kind of problems. And for r equals 1/2, what we're going to do is we're going to put in, I'll come back to that, hold on. We're going to put in here in this recurrence relation, we're going to let r equal 1/2. Okay, we're going to substitute 1/2 for r. And so when we do that, this is the resulting recurrence relation. Now we can do a little algebra on this. And when we do the algebra, it turns out that C sub k will equal negative C sub k minus 2 over k times, over in the denominator, k times the quantity 2k minus 1. And that's for k equals 2, 3, 4, and so forth. Absolutely beautiful, right? Absolutely beautiful. Okay. We have 2 pages left here. 2 pages left. And once I'm done, I'll make your exam 3 grades visible to you. I'll make comments about exam 3 in the next class. A few things I want to talk about here or there. But overall, the grades were good. The median was 91% for exam 3, just to let you know. Okay, may I move to the next page? Don't want to rush anybody. Okay, Zachary says no, no. Okay. You know. Okay, all right. Good, Matthew. Good, Antonio. So let me know, Zachary, when you're ready to go. All right, very good. Thank you. All right, so now this is just like, we're going to let we're going to let k equals 2, k equals 3, k equals 4, right? We're going to, but remember, c sub 1 is 0, okay? And incidentally, we are going to let c sub 0 equals 1. And you can just solve for the coefficients. Okay. And it turns out that all the odd powers, okay, all the odd powers, I mean all the odd coefficients in the power series are going to equal 0. Now when r equals 1, you'll have, again, the recurrence relate. You substitute r equals 1 into that recurrence relationship, and then you're going to get some new coefficients for c sub k, for different ones, because it's for the other power series. These coefficients here, all these coefficients here are for the first power series, and that was for when we let r equals a half. Then now we're going to let r equals 1 and get a new recurrence relationship, and that'll allow us to get the terms of the power series when for the second power series. So really, I'm just going to let you copy here. Okay, we have one more page to get to. Let me know if you have any questions.
So Professor, you said we couldn't let C0 to be 0.
That's correct.
And well, we'll only be able to let C0 to be 1.
Well, we could let c sub 0 be any number, but let's let it equal 1. That's nice and easy. And WebAssign, the answers, are very specific to what your coefficients are.
Okay. So
Good
what about
question.
C1?
C1, we're letting that equal 0.
Okay, but there was also uh uh an expression multiplied by C1, an expression of R multiplied by C1. So
Well, yeah, and
we only
well,
use the part which is multiplied by C0 to determine what the value of R is.
I'm sorry, right, correct. We only use the fact that that constant term had to equal 0 to solve for R. That's correct. Back
Okay,
in the that's right.
okay, thank you.
Good question. Good question, Michael. All right, are we how are we now? Are we ready to go to the last page? So you're going to have your homework for Thursday is on some section 6.3, right?
Professor, another
Yeah,
question.
sure.
It's the two values of R that we use to get the two equations. It's
That's
not
correct.
this time it's not interchanging values of C0 and C1. Am I right?
Well, that's correct. That's correct. Yes, that's correct. The fact that you have this variable R that has two different values makes it so that you'll get two different power series solutions as well. But that's correct. Very good. Very good.
So you also mentioned the fact that if they differ by an integer, if the R values differ by an integer, you may not have a power series of two. That's two power series.
You may not have two power series solutions. And that's they mentioned this, and I've moved to the last page, class, for you to copy. I think everybody's good. Go ahead and copy this. Michael's question, yeah, they talk about that before example 5, but we're like in the homework, we're keeping things simple. Okay, we're keeping things simple. So I don't think you're going to have to normally worry about that in your homework. Okay, we're really just, this is a differential equations. I mean, you can get a PhD in differential equations, and you can, there's more, and there's, after this, there's partial differential equations. There's a lot of other, so, but we're just keeping it simple, and it'll be good for applications, what we're doing. Very good question. Very good question. So now, class, we get the coefficients for the second power series, and again, I'm going to let C sub 1 equals 0. So this does work a little differently than section 6.2. And now now, hold on here. Hold on. I had this wrong. It's C sub 0. Hold on. C sub 0 equals 1, right? So for the previous power series, I hope I wrote C sub 0 equals 1. I meant that. So now the general solution, so like, in WebAssign, when you're finding solutions, they give you multiple choice, and they give you all these different choices. The choice we would want would be this choice, where we have a big C1. So the general solution is a linear combination of the power series. Okay, the first power series correspond to R equals 1/2, right? And so that's factored out of the power series, and then this is the power series. Here are the terms. And then the second power series had a factor of, x to the rth power, x to the first, R equals 1, times then this power series. Absolutely beautiful. How many think this is like really, really cool. I was hoping I might get a few more responses. Okay, thank you, Christopher. All right, Paige. Well, you'll get more comfortable with it, Paige. You will. Thank you, Matthew. Are there any questions? I'm going to leave this up, this page, but are there any questions before I stop the recording?
So instead of switching the C sub 0 equals 1 and equals 0 in both solutions, we're just letting the difference in R vary the outcomes?
The difference in R, that's right, Antonio. We're letting C sub 0 equals 1 and C sub 1 equals 0. And then the difference in R gives us it makes it so we can get the two different power solutions. That's right. See, we didn't have an R back in section 6.2. You didn't have a R.
Right. But
That's exactly
why wouldn't
right.
you get even like additional different solutions with different starting conditions, I guess?
Well, it just doesn't, the way the theory works is that it's all based on solving that indicial equation. The indicial equation, we said we won't let C sub 0 equals 0, so we could solve for R. So we let C sub 0 equals 1. And then we're going to let C sub 1 equals 0. And that's all you need to do. It's all you need to do in order to get I mean, you need two different power series solutions, and the fact that the two power series solutions, the R equals a half, gave you one power series solution, right? And R equals 1 gave you the other power series solution. So that's how it works in this section 6.3. All right, Antonio's good. Excellent. Okay, let me stop the recording. Very good question. Let me stop the recording.